Stochastic Processes, Module 9, Branching Processes. In the Module 1, we have discussed a review of probability. Module 2, we have introduced the stochastic process. Module 3, we have discussed the stationary processes. Module 4, we have discussed the discrete time Markov chain. Module 5, we have discussed the continuous time Markov chain. In the Module 6, we have discussed the martingale. Module 7, we have discussed about Brownian motion or Vernier process. Module 8, we have discussed the renewal process. In this module, we are going to discuss the branching processes. It covers 2 lectures. In these 2 lectures, we are going to cover the definition and examples of branching processes. 2 important branching processes, Galton-Watson branching process and Markov branching process are going to be discussed. Important measures like perform probability of extension, limit theorem, limit distribution and mean of branching process will be discussed. In the lecture 1, we are going to start with the introduction to branching processes. Followed by that, we are going to start the Galton-Watson process. Few examples will be discussed. Then we are going to discuss the probability generating function of Galton-Watson branching process. Then we are going to discuss the criticality and probability of extension. Watson in 1974 presented a solution to the problem of extension of families, which is as follows. Let P0, P1, P2 be the respective probabilities that the man has 0, 1, 2 and so on sons. Let each son have the same probability for sons of his own and so on. What is the probability that the male line is extinct after R generations, and more generally, what is the probability for any given number of descendants in the male line in any given generation? Watson gave the solution. Every family will die out even when the population size on the average increase from one generation to the next. Galton prefaced to the solution by Watson, and Galton recognized that a first step in studying the hypothesis would be to determine the probability that the ordinary family will disappear using fertility data for the whole population. The mathematical model of Galton and Watson is known as a Galton-Watson branching process. In 1938, Kolmogorov was also treated the above problem and determined the asymptotic form of the probability that the family is still in existence after a large finite number of generations. The branching process is a system of particles or individuals or cells or molecules which live for a random time and at some point during lifetime or at the moment of death produce a random number of progeny. Processes allowing production of new individuals during a parent individual's lifetime are called the general branching processes. Examples: populations of higher organisms like vertebrates and plants. Processes that assume a production of progeny at the terminal point of the parent entity's lifetime are called the classical branching processes. Examples: populations of biological cells, genes or biomolecules. One of the important notions in the theory of branching processes is that of the type space. The type space is the set which can be finite, countably infinite or continuum of all possible varieties of particles including in the process. Particles of a given type may produce particles of a different types. Restrictions on the type transitions as well as on the type space lead to different properties of resulting processes. Now we are going to discuss the classical branching processes. Consider a classical branching process in which progeny are born at the moment of parent's death. The distribution of particle lifetime tau has much impact on the behavior and analysis of the process. If tau is equal to 1, then it is called a Galton-Watson process. If tau is exponentially distributed random variable, then the resulting process is called a Markov branching process. In this model, we are going to discuss in detail Galton-Watson process and Markov branching process. If tau is an arbitrary non-negative random variable, the resulting process is called age dependent or Bellman-Harris process. Now we are going to discuss Galton-Watson process. In the next lecture, lecture 2, we are going to discuss Markov branching process. Consider particles that can generate additional particles of the same kind. An initial set of particles which we call the 0th generation having offspring that are called first generation, their offsprings are the second generation, and so on. We denote by Z0, Z1, Z2 as the number of particles in the 0th, 1st, 2nd generations. Please see the illustration. This is Z0, Z1, Z2 and so on. So, this is a illustration of the number of particles in the first generation, 0th generation, first generation, second generation and so on. Furthermore, we make the following assumptions. If the size of the nth generation is known, then the probability law governing later generations does not depend on the sizes of generations preceding the nth. It means the sequence of random variables Zn form a discrete time Markov chain. We make additional assumption that the transition probabilities for the Markov chain do not vary with time. It means the sequence of random variables Zn is a time homogeneous discrete time Markov chain. We have discussed the discrete time Markov chain in the module 4 in detail. Note that the number of offsprings born to a particle does not depend on how many other particles are present. Also, we assume that Z0 is equal to 1. In the illustration also, we made it Z0 is equal to 1, Z1 is a random number of particles, Z2 is a random number of particles and so on. If Zn is equal to 0, then the probability of Zn plus 1 equal to 0 is equal to 1. The probability distribution of Z1 is given by, the probability of Z1 takes a value k, that is nothing but in notation p suffix k, and the summation of pk's is equal to 1, where pk is the probability that a particle existing in the nth generation has k offsprings in the n plus 1th generation. So, this is the probability mass function for the random variable Z1. It is assumed that pk is independent of the generation number n. The conditional distribution of Zn plus 1 given Zn is equal to k is appropriate to the assumption that the different particles reproduce independently. That is, Zn plus 1 is distributed as the sum of k independent random variables, each distributed like Z1. Since the sequence of random variables Zn is a time homogeneous discrete time Markov chain, the one-step transition probabilities are given by p suffix I comma j, that is nothing but the probability that Zn plus 1 is equal to j given Zn is equal to I. That is same as y1 plus y2 plus and so on plus yi, that takes a value j for I comma j belonging to 1, 2 and so on, where yi's are IID random variables, each distributed like Z1. So, the illustration for the Galton-Watson process is Z0 is equal to 1, Z1 here it is 4 and Z2 is 7 and so on.